So welcome back. So we are into the third week. As I mentioned in my earlier class that from this section we will be talking about, before I get into in-depth detail of what is a quartz crystal microbalance. I believe most of you in your 11th or 12th standard must have heard about piezoelectric materials. At some point or other must have heard. So, piezoelectric materials are those materials, just for your recap, when you compress them or you put pressure on them, they generate electricity or they generate some kind of a current, or there is a change in voltage. Some kind of electrical output is being obtained when a material is compressed. So, in other words, what is exactly happening when I am telling you this? So, say for example, there is a material like this, okay, and the atoms within it are spread out like this, okay, and suppose you have two electrodes on both sides. So, this is say E1 and this is say E2. Now, you are compressing this. So, this is its nature. So, you are putting compression. So, when you are compressing this, what will happen? These atoms will starts to come close to each other, and E1, this is your E2, and this is the zone where you will observe a change in either the voltage or the current across this material. These kind of material are piezoelectric material, and quartz crystal microbalance, QCM commonly called, is a material which exhibits such piezoelectric properties, and such piezoelectric property could be utilized for a sensor. So, now let us go to the details of it. So, here is a name I mentioned, Sauerbrey equation. So, Gunther Sauerbrey in 1959 during his PhD work gave the whole idea of quartz crystal microbalance. So, what you see here is a quartz crystal, and these are the two electrodes across it. So, a schematic illustration of the quartz crystals of thickness H, you see the thickness H and a mass M, okay, and excited to a resonance frequency by the application of an alternating voltage. An oscillating crystal with added mass. Now, the thickness is H plus H and mass is M plus M. So, now what exactly does that mean? So, say for example, you have a something like this, okay. This is a quartz crystal, fine. Now, I put a mass on top of it like this. That is exactly what you are seeing in the slide. Once I put a mass, this exactly is the situation when I drew. This mass will compress this thing, and during this phase, there are two things which could happen, okay. Either this will generate a current, or I can do it the other way. I can give a current and I should be able to see some kind of a change out here. It is a vice versa process. And when we talk about a Sauerbrey equation actually is the basis of the quartz crystal microbalance, and the parameters what you have to understand is, and I will come again into this, resonance frequency, fundamental resonance frequency 1 upon S, harmonic number, wave velocity in the quartz plate, thickness of the quartz plate, as you could see the thickness, total added mass, an active area and active mass. And I will come to that in a second again to this slide. Before that, let's talk about what really quartz crystal microbalance is in a dry sample, oscillation and Sauerbrey equation. So, molecular adsorption via vacuum or gas phase typically results in a rigid film that are fully coupled to the oscillation of the electrode surface. Hence, a change in mass of such film is linearly related to the change in the oscillation frequency, which is defined by the well-known equation called Sauerbrey equation. What does that mean? So, say for example, here you have a quartz crystal and this is say vibrating in its natural frequency. Now, say for example, I put a mass. So, what will happen? Suppose this is moving like this in a natural frequency. The very moment I put a mass, the frequency is going to come down. Okay. So, that is exactly what is being said here. Hence, the change in mass of such a film is linearly related to the change in oscillation frequency. So, if oscillation frequency is say nu, it will be directly proportional with the mass which is being added. The QCM can provide useful information on the amount of mass deposited and the rate of deposition or removal of such films by monitoring the real time change in the frequency. So, the change in frequency of with which that balance crystal is oscillating will tell you that how much mass has been added and how much mass has been removed. The theory and instrumentation of QCM is Quartz, the piezoelectric resonator. So, if you look at it, it is basically what it says is the operation of the QCM is based on the piezoelectric effect that occurs in crystalline material of certain crystallography known as acentric materials. Quartz belongs to this class of crystal. The word piezoelectricity is derived from Greek word piezon, which means to press, and the electricity that is generated in response to the applied pressure in these type of materials. Now, having said this, let me go back to this slide. So, when you press, and you can press in multiple ways, you can add a weight onto that. You are basically pressing it. Okay. If you add something, so what will happen? Its frequency is going to change. So, depending on the mass what you are adding, the frequency is going to change. It will decrease or increase, but it is going to change. So, piezoelectricity is defined as the generation of electricity in response to the mechanical deformation caused by the mechanical stress or as a generation of physical deformation on the application of electricity in such crystal. The French physicist Pierre and Jacques Curie discovered this effect in 1880 when they demonstrated that salt crystals could produce electricity when deformed along certain crystallographic orientation. A year later, they demonstrated that the converse effect was also possible, that is, a quartz could deform upon voltage application. This is exactly what I was trying to tell you in the first slide. So, say for example, across this out here, first I showed the case of when you are compressing it. So, this is a case of compression, right. Now, say for example, instead of compressing, what you start to do, you apply a voltage across it, something like this. Okay. These are the two wires, my fingers are the two wires. Okay. Now, you apply a voltage across it, there will be a compression, there will be a change in its structure. So, it is reverse both ways. You can generate electricity by compressing it, or you can give it electricity to compress it. So, you can physically compress the material, it will generate electricity as I showed you in this cartoon, where you have the molecules arranged like this before compression. After compression, they are close by and they generate electricity. You can exactly achieve the same thing by a reverse way. You can apply current across it and they will reach to that particular deformity. So, this is the beauty of piezoelectric material, and using quartz crystal microbalance was for measurements of weight in terms of frequency was the PhD thesis of Gunther Sauerbrey in 1959. Based on that principle, what we today talk about, QCM, quartz crystal microbalance, have been developed. So, coming back where I was, so once again, the operation of QCM is based on the piezoelectric effect that occurs in the crystalline material of certain crystallographic known as acentric materials. So, remember this part, okay, acentric materials, and basically which means to press, and the electricity that is generated is in response to applied pressure in this type of material. So, this is the fundamental basis. Once you have understood this, now let us look at the theory, how it looks like. So, here you have the metal coating is the quartz crystal. So, here if you follow the color pattern, here you have the quartz crystal sitting out there, and these are the electrodes. I just mentioned the E1 and E2 for your understanding from the previous picture. And what exactly happened is that design of the quartz crystal with electrodes, top view and the bottom view are schematic illustrates the strain induced in an 80 out of crystal application of AC voltage, as you could see, and a schematic illustration of how amplitude of vibration varies with the distance from the center of the sensor. The area of vibration is called active surface area and sensitive to mass change. So, extremely important part is this part, exactly where the major sensitivity happens. So, the major sensitivity, we look at it, is here, and it dampens down in both sides. Realize? So, it is at that peak, that particular node, you see the maximum. So, it is a function of the space. There is a unique active surface versus the corners where you do not see that kind of sensitivity. Now, when we talk about the mass sensitivity of QCM and Sauerbrey equation, so here it is, the frequency change in the QCM can be measured with a resolution of 1 Hertz or less on crystals with fundamental resonance frequency in the megahertz range. Because of its high stability as a resonator, quartz crystals were successfully incorporated in the early 1900s as a component of various devices such as electronic filters, frequency control devices and ultrasonic transducers. The application of quartz crystal as a sensitive mass balance was realized in the late 1950s following the pioneering work of Sauerbrey. Sauerbrey demonstrated in 1959 that frequency change delta F of the quartz crystal is linearly related to the mass change. So, there is a relationship between delta M and delta F, and the equation Sauerbrey developed is this: delta M is equal to constant. I'm not getting into the derivation, I will give you a reference, you can look into it, 1 upon n, where n is the overtone number, multiplied by delta F. So, you can write it like this: delta M equal to minus C upon delta F. This is the equation. So, equation typically referred to as Sauerbrey equation constitutes the basic principle of QCM technology, and overtone is any resonant frequency above the fundamental frequency of sound. When we talk about the overtone, it is something like any material, anything has a fundamental frequency, the base frequency. Overtone is anything above the base frequency, and that is called overtone numbers. And there are overtone singing. If you guys go to YouTube and give a search, overtone singing, there are some really wonderful videos which will talk about the overtone singing, especially if you have heard about the singing which are done in regions like Tibet and in the Himalayan region, that humming sound, those are overtone singing. In several places of the world, Tibet, in the higher ridges of Himalayas, if you go to Himachal Pradesh, there are places where overtone singing is being followed. It's a kind of a prayer. So, where you could see the overtone singing happening. So, if you have to understand what is the basic concept of overtone and how it influences the voice modulation, then I will recommend you guys go and see some of the wonderful videos which are there in YouTube channel, and you will get a very clear idea what is this N stand for, which is the overtone number. Thank you.